Hey guys, welcome back to the Dynamics video series. In this video, we're going to be talking about free fall or just general kinematics. I think we're going to focus on free fall for this video. So we're going to be doing problems that have to do with things that are the only force affecting them is gravity. Right? That's essentially what all free fall is. If you noticed, I've added a couple equations on the left side or on the right side. We have these. So these are what are called the constant acceleration equations, right? And you can always use these for kinematic or kinetic problems when you have an acceleration that stays constant, so a non-variable acceleration. Now, since for free fall, the only force acting on a body or an object that we have is gravity, and gravity is constant for anything near the surface of the Earth, or almost completely constant. We're going to treat it as constant. We're going to go ahead and be able to use these equations for all of our problems that we're going to do today. All right, so let's work on this first problem. So if you want to throw a ball from a standing height of 2 meters, right, and the ball is moving upwards at 20 meters per second, right, we want to figure out two things. First, how long will it take the ball to reach the max height? And then what is the ball's actual max height? All right, so how do we get started? So we have to analyze what we mean by max height, right? So let's say I have a ball here, right? Good drawing of a ball, and I'm throwing it up at some speed, right? Straight up, and eventually it's gonna get up here at its max height. So what are the characteristics of the ball initially, so down here, and at the max height, up here, right? So initially, the position of the ball we do know, right? So we can say the position or not, right? That's what the initial position means, or what the XO means in this equation, is equal to 2 meters. We got that just because we're throwing it from a standing height of 2. That tells us that the initial height is 2, right? Do we know the height of this yet? The X? No. We want to solve for that in part B, so we don't know that yet. So we'll leave that as a question mark. What else do we know? We know the initial velocity. Right, so the velocity not here was given to us at 20 meters per second. So we can write that as well. And the velocity up here, do we know it? It wasn't stated in the question, but do we know it? So if you imagine anything going up to its max height after you throw it up, right? You're throwing it up. It's at its max height. What does that mean? That means it's no longer translating upwards. Right? And if it's no longer translating upwards, and we had that initial velocity going upwards, we can know that at this point, the point at which it just stops, right, at the top, the velocity has to be 0, right? And then it starts accelerating downwards due to gravity and all that, so it gets another velocity going down. But for the moment that it's at the top and it meets its max height, the velocity is 0. Okay, so we know that. So knowing that, which equation do you guys think we would use to solve part A? So part A is asking for how long will it take the ball to reach the max height? Think about it. If I had to pick one, I would say this one right here or the second equation. Why? Because we know a lot of things in this equation. We know the velocity at the top, we know the initial velocity, and we know the acceleration, right? Because the acceleration is always just gravity in a free fall problem. What we don't know is time, or the initial time, and that's what we're looking for in this problem. So I would pick this equation, right? So let's write that over here. The velocity final equals the velocity initial, v naught, plus our acceleration times time. The reason I'm writing just t here and not t minus t naught is because usually we can take our t naught to just be equal to 0. And that's what I'm going to do in this case. So subtracting 0 from anything doesn't change it, so I'm going to leave it as t. So Vf minus V naught plus A times t is our equation we're going to use. So I haven't explicitly written out the value we're going to use for gravity or the value we're going to use for acceleration. So let's think about it. What number should we use? We have two numbers. We can either use the metric unit or the customary unit. Since we see that our problem is in meters, right? We know we're going to be in metric. And so the value of G in the metric is 9.8 meters per second squared. Right? That's how much gravity is accelerating you at any point if you're on Earth's surface. So let's rewrite this equation, right? This is going to become the velocity final equals the velocity naught plus, I'll leave it for now, gravity times time. So the reason I'm not putting a plus initially is because here is actually a minus, right? Reason for that. So I didn't establish an axis yet, but I'm going to draw it here now. So I have this axis, right? Things are only moving up or moving down, right? And since we have to have a vector, right, because velocity and acceleration are both vectors, we have to have a sign convention. So one of these has to be positive and one of these has to be negative. Just for the sake of simplicity, and I feel like it's most intuitive, we're going to say that the positive direction is going to be the upwards direction, and the negative direction is going to be the downward direction. So now let's look at our vectors and let's see what they are, right? So our velocity initial, right? Is it moving up or is it moving down? I'm talking about this initial velocity. The initial velocity is telling us that we're going upwards, right? And we just said upwards is positive. So this is a positive 20 meters per second, right? Now what about gravity? So now down here, right? Gravity is always pointed which way? It's always pointed towards the earth or downward. And because it's pointed downward, based on my sign convention, this gravity number is going to be a negative 9.8 meters per second squared, right? And when I translate that into this equation I wrote over here, that positive becomes a negative. All right, so that's the reason for the positive and negative. Now let's plug in our numbers. So we know our velocity final is 20. Or sorry, not 20, 0. Our velocity initial was 20 minus our gravity, which is 9.8 times time, which is we don't know. All right, so what's the next step? Now we just have a one equation with one variable in it, so we can solve for time. I'm going to use a solver and just tell you now that our time value is equal to 2.04 seconds. All right, so that's our answer for part A. Let's move on to part B. So what is the ball's maximum height? Now we're going to use our a different equation than we used last time, because now we want to know its position, right, or its position value when it's at the max height. So how can we do that? Which equation do we think we should use now? Exactly. I know all of you said we should use the top one. Why? Because that's the only one that has position in it, right? And we want to find position. This is what one we should use. So this equation, I'll write that down here, is just the same as saying that's the final position, right? The x on the left equals the initial position plus the initial velocity, right? Is that what I wrote? Oh, v naught I wrote. Times time plus 1/2 the acceleration t squared, right? So this is the same as that first equation. I just truncated the t's by turning the t naughts into 0. And now we can plug values in here and solve for our value. So let's see what we're going to get. So our x final, which is the x we're looking for, is going to be the same as, so our x naught was given as 2 meters. That's the height we threw the ball from. So 2 plus our v naught, which was 20, times our time, which we just solved as 2.04. And then plus our 1/2, right? Our acceleration is gravity. So I'm going to write in the negative this time explicitly with the gravity. So negative 9.8 here. Remember that vector is going downward. And then times our time squared. So 2.04 squared. Perfect. And now again, right, we have one equation with only one variable in it. So I just plug and chug this stuff into a calculator. And then after you do that, you'll get eventually that your x value or your position value, right? You could also write y here if that's less confusing, but you can use them interchangeably. It's going to be equal to 22.4 meters, right? And I solved that using a solver. All right, so that's this problem.
Okay, so this second free fall problem is going to be a little different.
So this is more akin to something you might see on a homework or on an exam, and it's not just going to be like a one-step plug and chug solution. We get an image for this one, so lucky us, but let's see what we can do. So we know that a boy is going to kick a ball at an angle at 45 degrees, and the ball is going to have a maximum vertical height when it clears the fence. We're going to take this 3 meters as the max vertical height, and we want to determine the time when the ball clears the fence, right? And it's giving us a range for a solution. How nice of them. All right, so let's see what we can come up with. So we got to remember our kinematic equations. So I'm going to pull those up, right? So here they are. Right, so these is what we know, right? This is what we can use here, right? Because this is a free fall problem, and gravity is constant, right? Let's look at what number our gravity is going to be. So in this case, we know that gravity is going to be in the metric system since our given units in meters. So it's going to be a 9.8. Okay. Let's figure out if gravity, we want it to be going positive or negative, right? So let's again draw our axis. So let's say up is going to be positive, and to the right is also going to be positive, right? This is not just one-dimensional motion. It's moving up and down and left and right, so we have to have two axes, right? So gravity is pointed in which direction? It's pointed downward. So this is actually going to be a negative 9.8. Okay. Let's continue. So what type of equation should we use here, right? What are we looking for? So we're looking for time, right? So let's see what we can come up with. So we're given a couple things. We're given, first off, that this angle is equal to 45 degrees, right? And we're given some distances, right? So not explicitly, but kind of. We're given that the velocity, right, of this thing at this point t, right, or at this point time when it's going over, horizontally, it's some number, but vertically, right, so in the y, it's 0, right, because it's at its maximum height. This is in the last problem. So let's see what we can do with that. So I want to use this second equation, right? It's going to be useful, right? So let's type it out. So our velocity at the end, right, or the velocity I want to talk about is VTY, right, because we know that one. And that's going to be equal to our initial velocity, right? Now, since our initial velocity wasn't only in the y, we have to do our initial velocity in the y, plus our acceleration times time, right? So let's figure out what we have to plug into here. So our initial velocity, our velocity at the highest point, right, at time t in the y is going to be 0, right? So I can just fill in a 0 here. Our initial velocity in the y, right, we actually don't know our initial velocity. We don't know this number. So we're just going to write our velocity initial. And then we have to remember how we represent this vector in just the y-plane, right? So it's going to be going this portion of this triangle, right? So if you imagine this vector coming out to here, there is an x component, right? Usually x is in this direction, and a y component, right? Y is going usually up and down, right? So in the y, right, we know our angle is 45 degrees. We know that this over here, this going upside, is the sine of 45, and this is the cosine of 45, right? VO. Oh, I'll just times VO here, right? So we know if we want to represent the vertical velocity, right, initially, then this has to be VO sine of 45. Perfect. And then we have our acceleration. Like last problem, it's just negative 9.8 because we chose it down, and then times our time, right? So we have one equation so far. Can we solve it? Well, let's do a check, right? We have one variable, two unknown variables, so you can't solve one equation for two variables. It would be impossible. The algebra wouldn't work. So we're not done yet. We got to keep going, but we know this is going to be one of our equations we're going to use towards the end, right? So let's see what our next one should be. So what do I want to do next? Let's think. I know something else, right? I know the distances, right? So I know the horizontal distance I want to travel, right? And I know this vertical distance, right? Which one of those could be helpful? Think. I would say the horizontal distance, right? Because there is no acceleration in the horizontal direction. Gravity is only acting on this ball in the downward direction. So we actually, if we wanted to use this equation, right, for the horizontal distance, then this entire term would disappear, right? Because we don't have an acceleration acting in that horizontal direction. So that's what I'm going to do here. So let's write it over here. So I want the x position, right, in the x. That's going to be the final, equals the x position initially in the x, right, plus our initial velocity in the x times time, right? And then over here, I would put this acceleration stuff, but since there's no acceleration or force acting on this body in the horizontal, I can just leave it alone. Right? Let me get rid of these yellow red lines. There we go. So let's fill out what these variables mean. So our x position in the x direction, right? Since we know that the x direction is this way, eventually it's going to get here. So it traveled 6 meters. So our number there is 6. And that's going to equal our x naught. Our x naught is just 0 because we started at, let's say this point was 0, 0, not moving anything left. So that was the initial position. And then plus our initial velocity. So our velocity naught in the x, again, it's unknown, our velocity naught. But to represent it in the x, since in the y it was sine, in the x it's going to be cosine, right, of 45 degrees. And then again times time, right? So now this is our next equation we're going to use. Now let's see if we can solve this system of equations, right? So we have 2 equations, and now let's count our variables. So we have 1, and this is the same variable. And then we have 2, and this is the same variable, right? So we have 2 equations and 2 variables, right? So now at this point, we can actually solve this using algebra. We know this is possible. Now first, I'm going to show you guys how I would solve it just algebraically. And then I recommend, honestly, doing it in the program that Dr. Everett lets you use, Mathematica. It's just kind of a plug and chug thing you can use to solve algebra really quickly on a test. So you don't lose those points in your exam for making a simple algebra mistake, for getting to carry a sign over or something like that. So I'll do it first algebraically, and then I'll show you guys the actual input on Mathematica. So first thing I would do is I'm looking for time, right? So that's the variable I want to solve for. So I'm going to rearrange one of these equations to solve for not time, but my other variable that I'm looking for. So let's say I'm going to rearrange this equation to solve for this one. So how would I do that? So I'm going to rearrange this equation. So I want to isolate this variable. So I'm going to move this entire term over to the other side. So this is going to become that V naught equals 6, let me erase this arrow, divided by the cosine of 45 times t. I'm going to extend this. Okay, now I rearrange that equation. I'm going to plug it back in over here where I have this VO, right? So let's see that down here, right? So where I had that VO, I'm going to plug in this term I just got. So 6 over the cosine of 45 times the time times the sine of 45 plus negative 9.8 times t equals 0, right? Because that's what this equation equals. So now let's simplify a little bit. So I have here a sine over a cosine on this side. So I can actually cancel those out. Well, not cancel out completely, but I can just turn this into a tangent, right? So these two become a tangent together. So I'm going to rewrite this as 6, the tangent of 45 times time, plus or minus, I'll just expand it now, 9.8 t, right? And now I can combine these. Oh, realized a mistake just now, earlier. Good job if you caught it. But actually, when I wrote this first equation, I was a little tiny bit Oh, wait, never mind. Sorry, there was no mistake. Okay, so let's keep going. So then this is going to equal 0, right? And I can move stuff around here. So let's move this 9.8 to the other side. So I have 6, the tangent of 45, t equals 9.8 t. And then I can, what can I do here? Oh wait, yep, sorry, one mistake. I was confused a sec because I was like, this might give me 0. But this t, I can't bring it up like that, like just I did. That was a very bad error. So let's move that down. So I'm going to erase this. So this is actually divided by t. And this is now the correct expression, right? And we can do some algebra here. So let's see what we can do. So let's say we're going to bring this to the other side. I need some space here. I'm going to go ahead and move this over just a tiny bit. So let's continue this here. So I'm going to move the 9.8 over to the other side and make it positive. So 9.8t equals 6 tan of 45, right, divided by t. Now I'm going to multiply both sides by t to cancel out this, right? And then now this becomes a t squared. Perfect. And then so now I have 9.8 t squared equals 6 tan of 45. From here, I can just divide by 9.8 and square root it. I'm kind of running out of room, so I'm just going to trust that you can do the rest on a calculator. I'm going to pull up the solved expression that I have for this. So solved, I have this Mathematica, which is the program. So we have this, and you can see that the answer is going to eventually end up being, if we had room for all the algebra, t is equal to 0.782461, right? Gives it very exact. I'm sure you can only do 2 decimals there, so you could probably write just that t equals 0.78 on any problem you get, and it would mark you as correct. So that's this problem solved. If you guys ever need help with either setting up your Mathematica or how to solve these types of problems, you go ahead and let me know. But that's going to be the end of the problem. Bye.